Yay!
Yay! Hey everyone, here's another example of a sort of a classic textbook problem. This one has been in just about every book I've seen, and this is a banked curve with friction. So suppose we're this little car, the little block, and we are on a curve, and the idea is, since we're on a bank curve and there's friction between the tires and the road, we can drive around this circle. We can drive around this bank, maybe in a path. I don't know. The path is going to look something like this, right? As we go around, so we can drive around with some speed. What we're going to do is we're going to solve for the maximum speed that we can go before we start to drift, right? And which way are we going to drift? We're going to drift up the plane. So we're going to find out what that is. Now, what we're going to also find out, just so you know, the reason they make these banks is so that you can go faster than you would normally. In fact, if there were no friction and the ground was flat, we kind of did this example before. If the ground is flat and there's no friction, you can't go around any turn, right? You just keep on going straight, tangent to the circle. But if it's banked, there's a speed that you can go, even if there's no friction, where you don't go up or down the plane. You can keep going around in a circle. Okay, so let's see how to treat it. Okay, first of all, let's draw the forces. So what's acting on the car? There's gravity going down. I'm saying that it's banked, it's inclined by an angle theta. Okay, this is like our inclined plane problem. Here's the normal force going up that way, right? And friction. Okay, so again, what I do is I try to imagine what would happen if there were no friction. If there were no friction and you're driving too fast, you start going up the plane, right? Relative to the plane, you start going up to the top. So friction must be keeping you there. So the frictional force is acting that way, right? Down the plane. Okay. Now, what you're probably thinking is, aha, I remember. When we had inclined plane problems, what we did is we twisted the coordinate system, right? We had x pointed down the plane and y pointed normal to the plane. And so you might be tempted to do that again. And again, you can do that. The problem is it's going to be more difficult. The algebra is going to be tougher. Remember why we did that. Why we pointed the coordinate system, the x-coordinate, down the plane is because that was the direction of the acceleration. That was the direction the thing was going to move. So that's the general rule. Wherever the acceleration is, because that's usually what we're trying to find, that's the direction we put the x in. Okay, if we're going around in a circle, we're not going up or down the plane. We're trying to avoid that. So what direction is the acceleration? Well, if we're going in a circle, the acceleration direction is towards the center of the circle, right? So what this is telling us is that what we should do is go ahead and just have a conventional coordinate system with x going right and y going up, because that's the direction of the acceleration. All right, so that's what we're going to do. So here's and that's another reason why I want to show you this problem, is because we established a rule on inclined planes that we twist our coordinate system. But there's always an exception, right? This is an exception to that rule. So because the acceleration is not pointed up and down the plane, it's pointed to the center of the circle, that's how I'm going to do my coordinate system. Okay, so let's do it. In the x, I'm going to have to write small. There might be a little bit of algebra involved, so I'll see if I can fit it all in just on this page. All right, first of all, what are these angles? If the bank goes down to 0, if theta goes to 0, then that normal force is going to be pointed straight up, right? So this must also be our theta. And then this is our theta as well, down to f. Okay. Okay, so f, what do I have? I want the x-coordinate, or the x-component, I'm sorry, the x-component of n, and that's opposite to the angle theta, because I want this part, and so that's going to be sine. So that's n sine theta. What else is in the x direction? It looks like I got a little bit of f, so that's positive xf, cosine theta, because it's adjacent. And looks like that's it. So this is going to be equal to mass times how the thing is accelerating. So a sub c, the center of the circle is also to the right. So this is going to be my m and my v squared over r. Cool. All right, so that's in the x direction. What about the y? So in the y, what do I have? It looks like I got n cosine theta is going up. Ooh, look at my f. My f, that'll be the y component, so that'll be f sine theta, but that's downward, right? That's in the negative y direction, so it's minus f sine theta. Ooh, and I got an mg. I got another thing, minus mg. And that should equal 0. There shouldn't be any acceleration in the y direction. All right, so it looks like I'm all set. Now it looks like it might get a little messy. What I'm after is the v. I want to know what my speed is so that I don't start going up the plane, my maximum speed. Okay, so I got an n in both equations. In fact, that f, I got lots of n's because remember what the frictional force is. The magnitude of the frictional force is mu times n, so there's a lot of n's. So I guess what I'm going to have to do is solve one of the equations for n and then plug it into the other one. All right, so let me rewrite the top equation. This is going to be n sine theta plus mu n cosine theta is mv squared over r. And then I got n cosine theta minus mu n sine theta minus mg equals 0. All right, so what I'm going to do, I guess, since the top equation only has a couple of terms on the left-hand side, the bottom equation has 3, I guess I'll do the top one. So this top one, let me rewrite just this one to make it easy. So n is going to be equal to, let's see, if I collect those terms and factor them out, ooh, I don't want to do that because this is the v that I'm after is in that equation, right? So it's this one, actually it's this one that I want to rewrite. That'll be the better one. And then I'll plug it into the top one. So let's rewrite the second one. I think that'll be better. I don't know. We'll see. We'll see if it's better. I think it'll be better. Okay, so this is going to be n times cosine theta minus mu sine theta equals mg. Let me bring that and ooh, I'm also off the page. Let me bring that mg over to the other side. So there we go. So let me divide. If I divide by the thing in parentheses, I'll have n by itself, right? And then I can plug that into the top equation. All right, so let's do it. So the top equation is going to be, I'm going to have mg sine theta divided by this business on the bottom, cosine minus mu sine, plus, looks like then I'm going to have a mu mg cosine theta, and then I'm going to have the same thing at the bottom, cosine minus mu sine. Now, a cool thing is that m is everywhere, so it kind of doesn't matter what the mass of the car is. That's a good thing. So you don't have to worry about big cars acting differently than little cars, so the mass goes away. And now, oh, this isn't even true. I already did the mg. Oh, the right-hand side, sorry, the right-hand side should be mv squared over r, right? mv squared, I plugged it into the top equation. Right, so still the masses go away. All right, cool. So I'm kind of all set. I want to just solve for my v. So my v is going to be equal to, it's v squared, right? So I'm going to take a big square root. So looks like I'm going to have g factored out and r, so rg, and what do I have? I got my sine theta plus mu cosine theta, and then I got to divide by cosine minus mu sine. Okay, cool. I think, unless I've made a mistake, I think that's it. I think that's it. Okay, So let's put some numbers in. Let's see what this speed is actually going to be. So let's put a banking angle of theta is, let's see, 25 degrees. What else did I use? R is like 50 meters. And then mu between the tires and the road is like 0.3. Let's use that. So if you plug those in, let's see, what did I get? I got 20.9 meters per second. That sounds like a reasonable thing. It's sort of a limiting speed to keep you from sliding up the plane. Right? Now, if you get a complicated answer like this, maybe you'd be like, is it right? And the trouble is, in life, there's no book, right? Hopefully you guys are going to do interesting things that nobody's ever done before. And so when you get to a certain level, you can't check in the back of the book anymore to see if you're right. You just have to trust that what you did was right. But there are things you can do to make it probable that you're right. So for example, let's look at this and let's see if this makes sense for situations that we've already encountered. All right. Here's one thing we could do. Suppose it wasn't banked. Suppose theta is 0. We've done that example before. If theta is 0, then it's just driving on a flat road. And we sort of already did it. I think we did that, and we might have also said that it was like a button on a turntable, but it's also a car on a flat road, right? Same physics. So let's see if we get the same thing. If theta is 0, check. If theta is 0, what do we get? Well, sine of 0 is 0. So those terms involving sine theta go away. Cosine of 0 is 1. So I'm just going to have just a mu, right? Cosine over cosine is just 1. So I'm just going to have V is the square root of mu RG. Right, that really simplifies down. That matches. Check. With a check mark. That matches what we got before. So it doesn't mean that you're right if you got this thing. It doesn't, but it does mean that you might be right? There's a good chance that you're right because it's got the right limiting behavior. As theta goes to 0, we get the right thing. It's something we've already done before. Let's try another one. What happens if there's no friction? We've sort of done this before. It was kind of disguised, but it turns out it's the same problem of I think we had a pendulum. So it's an object going around in a circle hanging from a pendulum. It also happens to be the same thing as a plane, because that tension force going up, that might be the lift from a plane going around in a circle. So anyway, we've done this kind of thing before. So if mu equals 0, so that means there's no friction. It's frictionless. So if mu equals 0, what's the speed that you can go around if mu equals 0? Okay, well, look at the formula. If mu equals 0, then the cosine and sine term go away. I've just got sine over cosine. That's just tangent, right? So V is just the square root of RG tangent theta. Check. That matches. If you look back at the one of our previous examples, that's what we got, right? So that's neat. So we got the same limiting behavior in 2 cases. Very cool. So it doesn't mean that you're right. I think it is right. But if you were doing this and didn't have the back of the book to check, this is one way that you can check if you have a reasonable answer. All right, neat. What else can we do? Oh, this is the maximum speed for which you might slide up the plane, right? If you go faster than this, you'll start sliding up the plane, up the bank. What about the reverse? If you go too slow, you could start sliding down the bank, right? You have to go a certain speed just to stay put. What happens in that case? In that case, what does it mean to slide down the bank? Well, what that means is, let me do it in a different color. If you slide down the bank, what that means is that the frictional force will be up the plane. All right, so what you're going to do is F is just going to switch sign. So I'll sort of leave this as an exercise to the reader. There's no use going through all that algebra again. But what happens is, the net effect is, if you switch the signs on those things, what you get is that you switch the signs on the mu. It's sort of like negative friction, kind of, if you think about it. So what are you going to get if you get that? If you put that in and you work through the problem, then what you should get is, I'll go ahead and keep it in a different color. What did I get? When I plugged in the opposite direction, I got like 8.5 meters per second is the minimum speed, or else you'll slide down the plane. All right, so this is a very standard example that I've seen in every textbook, but it's usually one of the challenge problems or something that's harder because the algebra is just a little bit more formidable to get there. But it's okay. We can handle all that. All right, on we go.